Hey there. So today we are going to talk about the correlation coefficient. For those of you that this is review for, great. Sit back, relax, and get another perspective on the correlation. For those of you who maybe had a little bit of a shaky foundation, well, you're in luck because I made this video. Because the correlation is super important to a lot of psychology. All right. So, just to just so we're all on the same page, correlation coefficient is one of many methods to describe how the relationships between variables behave together. We can think about the correlation as a way to measure a relationship versus a regression, which is about modeling that relationship. But let's back up a little. So covariability, which is very similar to variability, describes how much scores are spread out or differ from one another, but it takes into account how similar these changes are for each person from one variable to another. So it's hello, Archie. Excuse me. So as changes are more consistent across people, from one variable to another, covariability increases. And so we can estimate this both with covariance and correlation. There are tons of ways, but the idea is we are quantifying a way of how variables move together. Hello. Yeah. Okay. Sorry for this distraction. It wouldn't be a video for me if there wasn't an unsolicited cat. Okay. Well, let's slowly move to the next slide. Okay, so we can think about the correlation as a standardized covariance. And Archie? Hello. What do you want? All right. So anyway, sorry I keep getting derailed here. So, a standardized covariance measure is exactly what it sounds like. It is a standardized metric so that we can look at how raw scores move together as a product of Archie, please. Oh my goodness. Okay. Let me collect myself. Okay, so we can use a number of formulas to calculate Pearson's correlation. The easiest one is to convert each raw score to a standard score, so like a z-score, and then multiply each pair of standard scores together. Essentially, that mean of the sum of cross products is calculated, and that mean ends up being the Pearson's correlation. You can think about it like the average standardized distance between our variables. So if we wanted to turn this into plain English, the idea here is that we want to know what a standard. Okay. Here's what we're going to do. I don't know what we're going to do because I just got totally derailed and I'm pretty sure I missed a whole piece of my notes here. Okay, so we're going to back up. Okay? We're going to back up to the beginning. I apologize. Archie? Oh my goodness! I'm filming! I'm filming! Okay. And we're knocking the camera out. Great. Okay. Here's what we're gonna do. We're gonna just keep him right here. Because maybe that will keep. Oh, now you don't like this? Huh? Okay. Okay. Let's talk about the correlation coefficient. Yep. Let's do that this time. So, the basic idea is that we are trying to describe the relationship between two variables. And there are a lot of methods to describe them and how these variables move together. Now, I'm going to focus here on the correlation, which is a method to describe how things move together. But we can also model how things move together using regression. Correlation would be God, Archie. Okay, this is my third attempt at recording this video. Attempt 1 was garbage just because it was. Attempt 2 and 2.5 had Archie just smother everything. Like there's still so much cat. But all I want to do today is talk to you about the correlation coefficient. That's it. That's it. Oh, it's in my coffee. Oh, sorry, there's cat hair everywhere. Alright, so let's talk about the correlation coefficient. Hopefully this is review for you. But if it's not, I'm really glad we covered it because it's a key aspect of much of psychology. So, the correlation coefficient is a way to measure covariability. Now, covariability, similarly to just general variability, describes how much a score is spread out or differs from one another. But it takes into account how similar these changes are for each person from one variable to another. Or at least that's the case with the correlation coefficient. So as changes are more consistent across people from one variable to another, covariability increases. And we often estimate this value, this description, using covariance or correlation. But if we want to perhaps model the relationship, that's when we move up to regression. Okay, so there are a ton of different formulas for how to calculate a Pearson correlation. The simplest one is essentially a standardized covariance, where we take a standard score for each value for x and for y, and then we multiply those two standard scores together. And that cross product of z-scores is a standardized metric to show how extreme values or unextreme values move together. So we sum those, and then to get the average, because if we don't, then the bigger the sample, the bigger the covariance. So we need to standardize it somehow. So what we do is then we average it. For a population level parameter, we would just divide by n. But for a sample, we use Bezel's correction and use n minus 1. That's the heart of this idea. It's the average standardized cross product. So for a correlation, the notation's pretty straightforward. We use Roman letters for samples and Greek letters for parameters. So for correlation, the sample statistic uses R, lowercase r, while the population parameter uses rho. It looks like a P, it's spelt RHO, and it's pronounced row like row versus column. And the beautiful thing about correlation is it's standardized and it is the same regardless of how you've measured your values. You could have measured them in height, in inches, or centimeters, and they will lead to the same correlation, as I've illustrated here with the correlation between parent and child from Galton's data, that anthropomorphic lab. We have some of that data here, and we can see that regardless of how it's measured, whether it's measured in inches, as in the top illustration, versus the bottom, which is in centimeters, they describe the same relationship. And it doesn't matter, which is great. Now, I had a little fun making this. This is so not helpful smart art, because it's unreadable, but it looks pretty. So sometimes PowerPoint. So I'm gonna be kind. So here are the basic properties of correlation coefficient. So it ranges from -1 to 1. And that the magnitude of that effect, so the absolute value of the correlation coefficient, indicates the size of the relationship. Larger values, so more extreme values, are those that are closer to -1 or 1. And frankly, at 1, it's a perfect relationship. I have some illustrations coming up as well as an optional activity that I will not do for you guys, but I'm happy to do it during office hours. But anyway, so correlation is measured this way. So positive values, so correlations greater than 0, indicate a positive relationship, versus correlations that are negative indicate a negative relationship. So for a positive relationship, as one value goes up, so does the other. For a negative relationship, as one goes up, the other goes down. Now, the magnitude of that. Oh, before I forget, sorry, I'm still discombobulated from Archie's chaotic interruption. Correlation is symmetric. So it does not matter if you were correlating y with x or x with y. The correlation's the same. A regression coefficient, not symmetric. But a correlation coefficient is. Now in R, we can use COV, C-O-V, or COR to obtain our measure. So COV is for covariances and COR is for correlations. So when we have two variables, we can separate those two indications with a comma, which is kind of nice. So check those notes out. Oh yes, I almost forgot. So the correlation is bound from -1 to 1, and a correlation of 0 indicates there's no linear relationship between the variables, while a correlation of 1 or -1 indicates perfect linear relationships. So I've illustrated some here. So correlations are commonly used to index strength and direction of the linear relationship between two variables. So here I've illustrated various correlation magnitudes. So correlation of -99 is practically 1. And as these numbers get closer and closer to 0, the spread around that data widens. And as you get closer and closer to 0, it's harder and harder to see that linear relationship until it looks like a circle-y blob. So here's more spelled out interpretation. So a perfect correlation for -1, for example, is a perfectly negative downhill linear relationship, while positive is perfectly uphill. Now a strong one, the rules of thumb are approximately 0.7 is a strong correlation. That approximately means that you explained about 49% of the variability from one metric to the other. Now, a moderate relationship is got a correlation of about 0.5. And negative means downhill, positive means uphill. A small correlation is 0.3. There are different rules of thumb, but that's the basic idea. Now, a small correlation only explains 9% of the variability from one metric to another. So that means 90% of it, or technically 91% of it, is unexplained. Most variables we look at in personality and other substantive areas I look at are in the small to moderate range. I've had a few huge correlations, so strong ones in like the 0.7, 0.9 range that weren't effectively like duplicate measures, and they were very strong effects, and those are rare. However, I want to illustrate here that correlations describe linear relationships. They do not describe any other kind of relationship. I've illustrated here a variety of correlations on the bottom row. I have some really nice structured data that have zero relationship in them because a correlation coefficient can't quantify that. And when it looks for a linear relationship, it finds nothing because there's not a linear relationship. Now, all of the lines in the middle column, except for the one in the middle, have a perfect relationship. It doesn't matter the steepness or slope. What does matter is how tightly bunched the data are, as we can see here. Cool. So that was my very, very, very brief correlation coefficient refresher. I'll see you later.